Let's talk about chemistry. It's the science that has literally built the world around us, from the fuel that gets you from A to B to the medicine that keeps us healthy. But what if that same science, the one that builds everything up, also holds the power to tear it all down? This is the big question we're tackling today. We're going to explore how chemistry is a real-life double-edged sword. It's capable of some truly incredible creation, but sometimes it leads to some serious unintended destruction. All right, so to really get a handle on chemistry's power, we've got to start with one of the most basic rules of the game, balance. Or, as chemists call it, equilibrium. Think of it like an invisible tug of war that's happening in reactions all around us, and even inside us, every single second. Now, the key phrase there is dynamic balance. When a reaction hits equilibrium, it's not like it just stops. No way. It's more like a perfectly matched arm wrestling match. Reactants are still becoming products, and products are still turning back into reactants, but they're doing it at the exact same speed. So the overall amounts stay the same, but the action, it never ever ceases. To really picture this tug of war, imagine a brand new store opening. At first, you have a flood of customers, the reactants, rushing in to buy stuff and become product owners. That's the forward reaction, and it's super fast at the start. But pretty soon, people start making returns. That's the reverse reaction. It starts slow, but it picks up. Well, equilibrium is at point when the number of people buying stuff is exactly equal to the number of people returning stuff. The store's still busy, but the net change in inventory is zero. So what gives chemistry all this power in the first place? Well, a huge piece of the puzzle comes down to one element, carbon. It has this unique superpower called catenation. It's just an incredible ability to link up with itself over and over again, making these amazingly long and complex chains and rings. This is why we have millions upon millions of different organic compounds, from gasoline to our own DNA. It's all thanks to carbon. And the most famous way we've harnessed this power of carbon is in hydrocarbons. I mean, these pretty simple molecules of carbon and hydrogen became the literal fuel and the building blocks for the entire industrial revolution and, the modern world as we know it. Yep, at its heart, it's really that simple, just carbon and hydrogen. But locked away inside their chemical bonds is a massive amount of stored energy. And their structures hold the potential to be remade into a crazy number of materials. They are the absolute foundation of our power grid, our cars and planes, and pretty much all of our manufacturing. So how do we actually tap into that potential? Well, one of the most important processes out there is called fractional distillation. Basically, we take crude oil, which is just this messy gunk of all different hydrocarbons, and we heat it up to about 400 degrees Celsius. This hot vapor rises up a huge tower, and as it rises, it cools. The bigger, heavier molecules with higher boiling points turn back into liquid first, way down at the bottom. The smaller, lighter molecules, they just keep rising until it's cool enough for them to condense way up at the top. It's actually a pretty elegant way to sort molecules by their size. And the results of this process are, well, they're everywhere. From that one batch of crude oil, we get gasoline for our cars, kerosene for jet fuel, diesel for our trucks and trains, and then the raw materials, the feedstock, to create this whole world of plastics, synthetic rubbers, detergents, you name it. Our entire modern infrastructure is basically built on these separated bits of oil. But, and you knew there was a but coming, here is where that sword cuts the other way. See, every single chemical reaction has products, and sometimes the ones you don't want to make are the ones that cause the biggest problems. The very act of burning these hydrocarbons to get their energy creates byproducts that have huge, huge consequences. Carbon dioxide gets all the headlines, but it is not the only thing coming out of the reaction. We're also pumping things like sulfur dioxide and different oxides of nitrogen into the air from our factories and our cars. And even though you can't see them, their impact is anything but invisible. This is a classic case of what we call secondary pollutants. The stuff coming out of the smokestack isn't the final problem. Once those gases get up into the atmosphere, they react with water vapor. Sulfur dioxide turns into the super corrosive sulfuric acid, and nitrogen oxides become nitric acid. These powerful acids then get mixed into clouds and, you guessed it, fall back to Earth as acid rain. And the effects are just devastating. Acid rain literally eats away at historic marble statues and buildings. It can turn beautiful, clear lakes so acidic that fish just can't live there anymore. In fact, it leaches aluminum out of the soil, which then clogs fish's gills, and they basically suffocate. It even poisons our water by pulling other toxic heavy metals out of the soil. This is a direct, destructive result of the chemistry that powers our lives. But these unintended consequences don't just stop at the local or regional level. Some chemical reactions have an impact on a truly global scale. They can actually change the fundamental systems that protect all life on Earth. So let's talk about our ozone layer. Okay, so check this out. Chlorofluorocarbons, or CFCs. For decades, we thought these things were a miracle of chemistry. They weren't toxic, they didn't catch on fire, and they were incredibly stable, perfect for refrigerators, air conditioners, and aerosol cans. The only problem was their greatest strength, their stability, was also their greatest weakness. They just didn't break down. They would just float around, slowly but surely making their way all the way up to the stratosphere. And once they got way up there, the intense ultraviolet radiation from the sun did what nothing on Earth could. It ripped them apart. This released a free chlorine atom, which is unbelievably reactive. It acts like a catalyst, kicking off this absolutely devastating chain reaction that just systematically shreds the ozone molecules that make up our planet's protective shield against that exact same UV radiation. So just how destructive are we talking? This number it's just staggering. 1. A single chlorine atom from one CFC molecule can go on to destroy over 100,000 ozone molecules before it's finally taken out of the cycle. That is an almost unimaginable level of chemical damage. And this isn't some abstract, far-off problem. A thinner ozone layer means more harmful UVB radiation gets through to the surface. That leads directly to more skin cancer and more cataracts in humans. It also damages our food crops, and it hurts phytoplankton, these tiny little organisms that are at the absolute bottom of the entire ocean food web. So this brings us all the way back to where we started. We've seen how chemistry can build empires of industry and energy, but we've also seen how its byproducts can threaten our health, our environment, and the very stability of the systems our planet relies on. And you see this pattern everywhere you look, right? We create chemical fertilizers to feed billions of people, but their runoff creates dead zones in our oceans. We invent these amazing plastics for everything from life-saving medical gear to computers, but now they pollute every single corner of the globe. We harness fossil fuels for incredible progress, but their emissions give us acid rain and drive climate change. For every promise, it seems, there's a peril. And that leaves us with this final, really critical question. Chemistry gave us the power to completely reshape our world, but it also gave us the knowledge to see the consequences of that reshaping. So, does that mean the responsibility now falls on us, the chemists, the engineers, the scientists, to pick up that double-edged sword one more time, but this time to consciously and very carefully design the new reactions and new materials that can maybe undo some of the damage and build a future that's truly sustainable? What do you think?